Welcome back to the aerodynamics class. In the last class, we were discussing about the thin airfoil theory, and we have the fundamental equation, right? And the equation is for um, you know the chord line where the vortex sheet is placed, right? And for that, the camber line is a streamline, right? So the camber line to be a streamline, we have arrived to the equation already, right? So let us continue that today, and we will. Our ultimate aim is to calculate the coefficient of lift and coefficient of moment. So today we will look into the coefficient of lift at least. I acknowledge John D. Anderson's Fundamentals of Aerodynamics, right? So So what we have done is, in the last class, we have calculated the induced velocity at the chord by having, say, I will once again write that, right? So I extend this, right? And this is Z and this is X, right? And we know that the vortex sheet is placed in the chord line. And we know the W is the induced velocity, and Z. So in this case, we have considered x comma zeta, where zeta is the dummy variable, right? And if one want to say this elemental distance, that can be d zeta, right? And we can write the distance like, so say if the point of interest is this, then this can be the zeta, and the x can be like the point at which we want to calculate the induced velocity. And finally, we have arrived with the fundamental equation 1 by 2 pi integral 0 to c, right? Gamma of zeta into d zeta by x minus zeta, that is equal to v infinity into alpha minus dz by dx. So we already know that alpha is the angle of attack and dz by dx is the slope of the camber line, and then the 0 to c is the chord, right? So we have arrived to this equation in the last class, and we had a discussion that when dz by dx is equal to 0, then it is a symmetrical airfoil, right? So zeta is a dummy variable of integration which varies from the chord length, like 0 to c, right? Then the vortex strength gamma of zeta is a variable along the chord line, and the angle of attack alpha and dz by dx is the slope. So now the point is, here it should satisfy a Kutta condition at the gamma of c is equal to 0, right? So let us have a discussion further we will apply this to the symmetric airfoil, right? We will apply this to the symmetric airfoil and we will calculate the lift coefficient, moment coefficient, and so on. Now, I said the vortex sheet is placed in the chord line and the airfoil is so thin. That means that this symmetrical airfoil is almost treated as a flat plate, right? So one can say that it is almost treated as a flat plate, flow over a flat plate, right? Anyway, so we will continue the discussion because the thickness, we have not considered the thickness, but we will consider the thickness later, right? So we also should remember that the expression which we have given is for the inviscid incompressible flow at small angle of attack, right? So now we want to calculate for the symmetrical airfoil, and I would like to have this zeta to be transformed into theta by considering a standard transformation. So I would like to express the zeta that is equal to c by 2 into 1 minus cos theta. So one can understand zeta is a dummy variable which is along the chord from 0 to c, right? So if you say theta, we already know theta varies from 0 to 180. So if it is 0, then the chord will be 0. I mean, the point at which we consider here it will be 0, and if it is 180, then it will become c. So with that transformation, we have zeta is considered as c by 2 into 1 minus cos theta. So here we can also say that x is fixed point, right? So in this case, x is a fixed point at which the induced velocity acts. So one can write the x as x is equal to c by 2 into 1 minus cos theta naught. So for our consideration, I have taken all these, right? Then if we want to calculate d zeta can be written from this equation as c by 2 sin theta d theta. So now we know the equation 1 by 2 pi, right? 1 by 2 pi integral 0 to c gamma of zeta d zeta x minus zeta, that is equal to v infinity alpha, because I consider symmetrical airfoil where dz by dx equal to 0. So let me write this full equation, that is 1 by 2 pi integral 0 to pi, right, gamma of theta sin theta d theta by cos theta minus cos theta naught, that is equal to v infinity alpha, right? So there is a rigorous solution for this equation, right? It can be obtained from the mathematical theory of integral equation, right? So which can be discussed further, but we will have a proof for this little later, right? So the gamma of theta, can be expressed as 2 alpha v infinity 1 plus cos theta by sin theta. I don't want to go deeper into the derivation part of this. If necessary, we will look into that later. But if gamma of theta, if you apply here, then you should get V infinity alpha, then the equation satisfies, right? So let us start with this discussion. Now, okay, we can verify this equation. Let us substitute gamma of theta into that equation and we will see. So this we can write 1 by 2 pi integral 0 to pi, right? So we have gamma of theta, sin theta, d theta divided by cos theta naught, theta minus theta naught. So we can write this equation by substituting the theta, gamma of theta. So 2 alpha V infinity into 1 plus cos theta. So I write this, I reduce this equation V infinity alpha by pi integral 0 to pi 1 plus cos theta into d theta divided by cos theta minus cos theta naught. So here it is theta naught, right? So there are various standard integrals. One can have that integral. So the mathematical integrals we need not to go further, but if necessary, please ask me. I can give the reference, right? So we can write that integral 0 to pi cos n theta d theta divided by cos theta minus cos theta naught can be written as pi sin n theta by sin theta naught. So let us use this, right? And we can go to the previous equation and substitute, right? So now this equation becomes V infinity alpha, right? So V infinity alpha by pi integral 0 to pi 1 plus cos theta, 1 plus cos theta into d theta divided by cos theta minus cos theta naught minus cos theta naught. So I will take this V infinity alpha by pi integral 0 to 0 to pi first integral d theta by cos theta minus cos theta naught plus integral 0 to pi cos theta d theta by cos theta minus cos theta naught. So we can reduce this equation, that is equal to V infinity alpha by pi, right? And here this can become, so this integral becomes 0 plus this integral, if cos n theta, if n is equal to 1 and this n equal to 1, then this become cancel and this become pi. So this is equal to V infinity alpha. So please note this V infinity alpha is what we have here. So by considering gamma of theta equal to 2 alpha V infinity 1 plus cos theta by sin theta, we have arrived to V infinity alpha, right? And hence the gamma of theta assumption is correct, right? Now we can go deeper into this particular gamma of theta later, right? And the standard integrals also we need to know, right? Again, we can derive the standard integral also, right? But that is not the goal of the present discussion, right? So we can now discuss that gamma of theta, right? So we already know gamma of theta, that is equal to 2 alpha V infinity into 1 plus cos theta divided by sin theta, right? Now, what happens if gamma of pi is necessarily the trailing edge? So it will become like 2 alpha V infinity. Here it will become 0 by 0. So it become indeterminate form, right? So let us apply L'Hospital's rule, right? And say for gamma of pi, finally we can arrive gamma of that is equal to 2 alpha V infinity, and we can write minus sin pi by cos pi, that becomes 0. So gamma of pi is equal to 0, that is gamma of trailing edge equal to 0, which satisfies the Kutta condition. Right. Now we have the relation gamma of theta, right? So ultimately we want to calculate the coefficient of lift, but you know very well that one want to calculate the lift per unit span, then they need to have rho infinity, V infinity, gamma. So in order to arrive this gamma, we have calculated the gamma of theta, right? Because the circulation varies along the chord. So let us write let us start calculating the gamma, right? So gamma is equal to integral 0 to c gamma of zeta d zeta, that we know already, right? So we already have enough information, and the equation can be transformed to theta variable, and then we can say gamma is equal to c by 2 integral 0 to pi gamma of theta into sin theta d theta. So we already know that, right? D theta equal to c by 2 sin theta d theta. So now gamma of theta can be applied here. Gamma of theta is equal to, so we can write c into v infinity. So gamma of theta is equal to 2 alpha v infinity. So I reduce this equation and write integral 0 to pi into 1 plus cos theta d theta. So that can be written finally as pi alpha c v infinity, right? Now we know gamma, and let us substitute this into L dash equal to rho V gamma. So what is L dash is equal to rho infinity V infinity gamma, and we can write that rho infinity V infinity and gamma is pi alpha C, and I will write this rho as V square, right? So this is lift per unit span. Then how about the coefficient of lift? Coefficient of lift. So coefficient of lift is CL, and that can be written as L dash by Q infinity S, right? Where S is equal to chord into 1, because you know already the span, that is S is equal to the C into B. This is B and this is C. So we consider chord into the unit span. So now we can calculate CL. Yeah. So let us write CL is equal to pi alpha C rho infinity V infinity square divided by Q infinity S, right? So Q infinity can be written as 1 by 2 rho infinity V infinity square into S is C into 1. So we can say that rho infinity V infinity square, then C. So finally we can arrive to CL is equal to 2 pi alpha, right? This 2 pi alpha is a famous equation, right? And also you should note that I have written C small l, right? CL, not CL. You know very well that the capital L represents the coefficient of lift of the whole wing, and the CL represents the coefficient of lift of the airfoil, right? So this is CL is equal to 2 pi alpha. Usually we used to calculate the, I mean experimentally also, we used to have the CL versus alpha curve, right? Say I am doing this for a symmetrical airfoil, right? Right. So this is for a symmetrical airfoil, and hence I can draw. So this should be 0, something like this, right? Now here we want to calculate the lift curve slope. So this is DCL and this is D alpha. So DCL by D alpha is equal to 2 pi. This DCL by D alpha is the lift slope, right? So it states that the lift coefficient is linearly proportional to the angle of attack, right? So it is actually supported by the experimental results also, because once you see this is a left curve slope, and at least before the stalling, this is really valid. So one can say that this dCl by d alpha is 2 pi per radian, or we can mention that as 0.11 per degree. And this is valid symmetrical airfoil, right? And before stalling. So in John T. Anderson have compared this with NACA 0012 airfoil, right? So we can have a look into that. So by this way, we have already come to the conclusion that CL is equal to 2 pi alpha, and dCl by d alpha is equal to 2 pi, right? So the next point is moment. So I think we can calculate the coefficient of moment in the next class, right? So I stop at this point. Thank you.